Okay, Assalamualaikum and good afternoon, everyone.
Waalaikumsalam, sir.
Okay, so today we will continue with our lecture last week on rotational mechanical system. So we will do tutorial on that topic, and then if you have any question, just let me know. Okay. Okay, so tutorial 4 is about rotational mechanical system. And let's look at the first question, question number 1. So find the transfer function theta 2 over tau A for the system below. Okay, so tau A is on shaft number 1, and theta 2 measures the angular position or displacement of shaft number 2. Okay, so this system has two shafts, meaning that there are 2 degrees of freedom. Okay, so let's look at shaft number 1, shaft J1. Okay, so from the question, it requires you to find theta 2 over tau A. So meaning that the input is tau A and the output is theta 2. Okay, so we use the steps that similar to translational mechanics. Okay, so let's look at shaft J1. Okay, so we draw the free body diagram of shaft J1. Okay, so we assume that theta 1 is the direction is counterclockwise. Okay, and on J1 there is one spring KR and one damper BR1. So this spring and damper will produce torque that oppose the motion of theta 1. So we have the torque from spring KR theta 1, and then the torque from damper BR1 theta 1 dot. And then the damper also connected to theta 2. So you need to consider the torque from theta 2 by the damper BR1. So we have BR1 theta 2 dot. And then the torque given tau A, the direction is against theta 1. Okay, the direction given by the question. So we have tau A clockwise. Okay. Okay, double check to see whether we have enough forces. Okay, so everything is there. Now we look at the second shaft J2. Okay, so theta 2 also the direction is counterclockwise. Now on J2 there is one damper BR1 and also a friction BR2. So these two will produce a torque or torques that will resist the motion theta 2. So first we have BR1, BR1 theta 2 dot, and also BR2. But BR1 is also connected with theta 1, so you need to consider the torque by theta 1. So we have BR1 theta 1 dot. Now we have all the forces and free body diagram. then we can write the equation of motions. Okay, so we start with J1. Oh, okay, sorry, I forgot to put the inertia. Okay, so we have J1 theta 1 double dot, and also here we have J2 theta 2 double dot. Okay, so we can write the equation of motion. So we have J1 plus BR1 and KR theta 1 minus BR1 theta 2 equals tau A and then we have the second equation. Okay. Now we need to convert this into frequency domain. So we have J1 S squared plus BR1 S plus KR theta 1 minus, or maybe if I write plus, minus BR1 S theta 2 equals tau A. And then we have here minus BR1 S theta 1 plus J squared S J2S squared plus BR1 plus BR2 theta 2 equals 0. Okay, then we can write in the form of matrix. Okay, so this is in the form of matrix. So the question wants theta 2 over tau A. So we find theta 2. So we replace this column into the second column of the big matrix. So I skip writing all this. I just write simpler. So in your exam, please write in fully. Okay, so you simplify the top one. Try to get theta 2 over tau A. Okay, any question for question number 1?
So I got a question for question number 1.
Yes.
In terms of its body diagram, isn't that the tau A in opposite direction? Shouldn't be that the value of the tau A should be negative?
Yes. Now the direction here is clockwise, while theta 1 is counterclockwise. So if you write this clockwise, counterclockwise, then you put negative. Understand?
Okay.
So it depends on the direction arrow that you draw. So if you draw clockwise, then tau A is positive. If counterclockwise, then you put negative. Okay, any question for question number 1 before we proceed?
Ada sir, saya.
Okay, so we move on to question number 2. So question number 2, find the transfer function theta 2 over t for the rotational mechanical system below, okay, above boleh lah. Okay, so here, if you look at this system, theta 2 here measures the position of a degree of freedom in between the spring damper and another spring damper. Okay, basically it measures this point here. So it's not measure the shaft. Okay, and here the shaft actually should have a degree of freedom as well, but in the question it doesn't give to you the degree of freedom for the shaft, so you need to add yourself a degree of freedom theta 1 here. Okay, so this theta 2 here similar to the lecture on translational mechanics, where there's a point here that has no mass, but there's a degree of freedom for that point. Okay, because one reason is because the spring and damper here is in series with spring and damper here. So if we can redraw this system, it should be something like this. Okay, so even though the damper here is pointing downwards or is connected downwards, but it doesn't matter. Okay, it doesn't matter because in what matters in this kind of derivation is how many things that are connected to the shaft or to the degree of freedom. So here in a new drawing, there is 1 degree of freedom theta 1 for the shaft, and there's another 1 degree of freedom at the point connecting two things in series. Okay, so we call it theta 2. Okay, so whenever there's a spring or damper, there's a spring and damper connected in series. So in between them, there should be another degree of freedom. Okay, just like in this example. Okay, so let's draw the free body diagram for question number 2. So let's look at the shaft theta 1 first. Okay, so we define theta 1, the direction as clockwise. So on theta 1, we have 1 spring and 1 damper connected to the shaft. So we have 1 torque from the spring, 1 theta 1, or I simply write theta 1, and then another one from the damper, so theta 1 dot. And then we have the torque, the input torque. So the direction is similar to theta 1 and theta 2. And now the spring and damper here is connected with theta 2. So there are 2 more forces from theta 2. So we have theta 2 from spring and theta 2 dot from the damper. Okay, so the 2 remaining things, spring and damper, are only connected with theta 2 but not connected with the shaft. So you cannot add the torque on the first free body diagram. Okay, now let's draw the second free body diagram. Okay, sorry, this one we have the torque, okay, the inertia. So theta1 double dot. Okay, so on the second free body diagram, the second degree of freedom, theta2, there are four things connected to this point. We have two spring and two dampers. So there will be four forces. Okay, so we have theta1 and another theta1, theta2. And then we have from the damper, theta2 dot, and another one, theta2 dot. Okay, we have two spring and two dampers. And then the spring and damper here is also connected with the shaft with theta1. So you need to consider theta1. So we have theta1 here and theta1 dot. Okay, so we have all the forces for both free body diagram. Then you can write the equation of motion and write in matrix form and find theta2 over t. Okay, so the most important thing is to get your free body diagram correct. Okay, so if you have your free body diagram correct, then the remaining calculation should be correct. Okay, should be okay. Okay, any question for question number 2?
So, macam mana nak tahu dia punya direction?
Direction yang mana?
Yang dekat yang dalam ni, yang macam theta 1 tu ada yang ke yang counter clockwise, ada yang clockwise.
Okay, so dalam ni macam soalan nombor 1 dia dah bagi dengan soalan nombor 2. Selalunya bila shaft 1 ni pusing ke clockwise, shaft 2 ni pun clockwise lah sebab dia center dia sama, center of rotation dia. So tak boleh lah shaft 1 pusing clockwise, shaft 2 pusing counter clockwise. Dia macam tak boleh lah, dia mesti pusing direction yang sama because the center of rotation dia sama. Okay, similar to question number 2. Later on when involves gearing, then the direction changes. Okay, like question number 3 later, like theta2 here. So theta1, the direction is in opposite direction of theta2 because of gear. So gear mengubah direction dia, while without gears, they should rotate in the same direction. Okay, any question? Okay, so you can try write this in matrix form, and if you are not sure, you can ask me later. Okay, so the most important thing is to get the free body diagram correct, because the matrix part, the Cramer's rule part should just involve mathematics. Okay, itu mungkin korang salah kira sebab careless ke. Okay, so I cannot help on that. Okay, but free body diagram should be correct. Okay, you must get it correct so that you can get the correct matrix and transfer function. Okay, so let's move on to question number 3. Okay, so question number 3 involves gear. So before we attempt question number 3, let's recap about gears. Okay, so let's jot down the formula for gearing. Okay, so the first formula is the gear ratio formula. So we have T1 over T2 equals theta 2 over theta 1 equals N1 over N2. And then the impedance transfer formula. Okay, so K destination equals K source times N destination over N source square. Okay, these two formulas are the most important for gearing. Okay, so let's try do question number 3. Okay, so find the transfer function theta 2 over t. Okay, so t is located on the left shaft J1, while theta 2 is located on the middle shaft. Okay, so here, first we need to decide which one we want it to be the destination. So usually we choose the destination as the location where the output that we want to determine. So here in this case, theta 2 is located in the middle. So we decide to choose the middle shaft as the destination. But it's not necessary to choose the middle shaft. Okay, but in this case, we can choose the middle shaft as the destination. Okay, so let's choose the middle shaft as the destination. So first, we need to transfer impedance from the other shafts to the middle shaft. Okay, so let's start with J, with the inertia J. Okay, so J equivalent equals J2 because we don't transfer the middle shaft, because the middle shaft is the destination. So first we transfer the first shaft J1 to the middle shaft. So we plus J1. So times the end destination. So end destination is 12. So we have N2 divided by N source, which is N1 squared. And then we transfer J3 to the middle shaft. So plus J3. So end destination is here 4 and 3 divided by N source is here N4 16. Sorry, N4 square. Now you can find the J equivalent. So we have 1 plus 2 times 12 over 4 squared plus 16 times 4 over 16 squared. So we have 3, 4, 20 kilogram meter squared. Okay, so that's for J. Now let's do for D. Okay, so D here is written on the gears. So D, like D1, D2, and D3 represent the friction effect of the gears. So similar like dampers, but it is friction. So here the middle shaft has already a friction D2. So we don't need to transfer D2, but we need to transfer D1 and D3 to the middle shaft. So let's calculate D equivalent equals D2. So plus D1. So times N destination, which is 12, divided by N source, N1 squared, and plus D3. So N destination is N3 divided by N source, N4 squared. Now you can find D equivalent. So we get 2 plus 1 times 12 over 4 squared plus 32 over 4 over 16 squared. So we have here 2, 4, 9, 13. Okay, correct me if I calculate wrongly, okay? Because I don't have calculator. Okay, now the shaft, the third shaft has a spring, but the other two shaft has no spring, and also the middle shaft has no spring. So we only need to transfer this single spring to the middle shaft. So we can calculate KE equals K times N3 over N4 squared. So we get 64 times 4 over 16 squared. So we get 4 Newton meter per radian. Then we have all the J equivalent, D equivalent, and K equivalent. Then we can redraw the system. Okay, so we have J equivalent with damper equivalent and also spring equivalent. And then we have here theta 2. So we need to transfer T, torque, because torque is located on the first shaft. So we need to transfer the torque into the middle shaft. So we need to use the formula, this one, okay? So let's say we have T2 here. So T2 equals tengok, N1 over N2. So we have N2 over N1 times T. So we have 12 over 40 equals 3T. Okay, so T2 here is 3T. Now you can draw the free body diagram of this new system. So on shaft JE, we have DE and KE. So DE theta 2 dot and KE theta 2, and the inertia JE theta 2 double dot. And we have the torque, which is 3T. Then we can write the equation of motions. So JES squared plus DES plus KE theta 2 equals 3T. So substitute the value JE, DE, and KE that we calculate earlier. So we get 20S squared plus 13S plus 4. And rearrange to get the transfer function. So theta 2 over T equals 3 over 20S squared plus 13S plus 4. Okay, so this is the transfer function theta 2 over T. Okay, any question for question number 3?
No, sir.
Okay, so for impedance transfer, you need to decide which shaft that you want it to be destination, and then transfer everything, including the inertia J, the damper, the spring, into the destination shaft. Okay, and you need to consider the gear ratio as well. Okay, so let's go for the next question. So question number 4, given the rotational system below, find GS equals theta 6 over theta 1. Okay, so here theta 6 is located on the last shaft J6 and theta 1 is located on the first shaft, okay, first part of the gears. So we have this gear and then another gear in between, 3 more gears. But all of them has no degree of freedom written on it. So you need to write your own degree of freedom. But it doesn't necessary because like these gears here, like this section until this section, they are connected with gears. Meaning that the rotation is having only 1 degree of freedom, which is theta 1. Okay, so let's go back to last week lectures that I skipped. So I skipped the last slide regarding how to determine the degree of freedom. Okay, so let's say you have this kind of system. There's a shaft here, a gears, and then right after gears, you have a spring before connected to a shaft. So let's say you fix the shaft 1 kg meter squared. Okay, so let's say you hold this shaft. So this whole system until here will become something like a wall, okay? Like rigid, cannot move. So if you treat this section as a wall, then this section here can move independently, meaning that this section has its own degree of freedom, independent of the gear rotations. Okay, so even though the gear is stopped, but this shaft here can move by itself, okay, because of it doesn't connected to the gears directly. Okay, so let's see what happens if we hold shaft 100 kg meter squared. So let's say if you hold this section here, then this part will become something like a wall. So if you rotate the gears, then this shaft here can still move independent of this shaft that is fixed. So all of this because of the presence of a spring right after the gears. So when there's a spring or damper right after a gear and then connected to a shaft, then the system can still move even though we stop the rotation of the gears. Okay, so therefore this system actually has 2 degree of freedom. So if you redraw the system by removing the gears, so what we need to do is we need to transfer impedance. So first we transfer impedance J to the other side. Okay, so let's look at the new figure. Okay, so when we transfer the impedance J 1 kg meter squared, so let's say this is the destination and this is the source. So to transfer this impedance, so we have J, let's say J1 equals 1 times N destination over N source squared. So we get 100. So this 100, you cannot add with this 100 because the degree of freedom is different, independent. So instead of adding, you draw a new shaft which has J equals 100, but you remove the gears and this shaft is connected to the spring. And then we transfer the torque. So torque T, let's say T2 equals T1 times N2 100 over 10. So we get 10 T1 or 10 T. Okay, so you transfer the torque. So you get 10 T. Okay, so the direction should be on the other side, but apa-apalah, boleh je. Okay, because theta 2 is in the same direction of theta 3. So let's say theta 3 is here. So theta 2 also the same. So when you transfer the shaft, the J, you remove the gears, but you draw a new shaft connected with the spring, okay, as if it is a new shaft, okay. So you cannot add this value here to this shaft on the source, on the destination. So all of that because of the spring is connected between the gears and the shaft. Okay, I hope you understand this part. Because we will look at, we will use this concept on the tutorial, okay? Okay, so let's look at question number 4 from the tutorial. Okay, so right after this gear number 4, there's no spring, but there's a shaft connected with a damper and spring, and then another shaft. So when you transfer the J and D, you cannot add D and J into this damper, for example, and this spring or this J. You cannot add them to this damper and J and spring. So you need to draw something else before the J. Okay, so let's do the impedance transfer. So because theta 6 is here, so we assume this section as the destination, and the other destination, the other section is the source. So let's transfer all the J. Okay, so J1, J2, J4, J3 represent the mass of the gears. So that's why it's written on the gears. Okay, so let's find the J equivalent. So J equivalent is equals to, so when you transfer all the J's, you can add directly on this J5. Okay, because this J5 is connected with the gears, but you cannot add on this J6 because of the damper and spring. Okay, so J equivalent will include J5. So JE equals J5 plus, okay, let's transfer J4 first. So J4 is already on this section, the destination. So you just plus J4. You don't need to do any gear ratio or impedance transfer. And let's do for J3. So J3, because J3 is located on the N3 gear, then you need to do impedance transfer. So we multiply by N destination over N source squared. And then we plus J2. So J2 is located here. So you need to transfer J2 to this section by multiplying the gear ratio N3 over N4. So not N2 because N2 is not connected with N4, but instead N3 and N4, they are connected. So you need to look for gear ratios for gears that are connected. Okay. So J2 will multiply N4 over N3 squared. And then lastly, we have J1 here. So plus J1. So J1, there are two gears, okay? Two gears are connected. So first one is N1 and N2. And second one is N3 and N4. So if you want to transfer J1 to the destination, you need to multiply the gears 2 times, okay? First is the N2 over N1 squared. So if you multiply N2 and N1, then you only transfer J into the middle section. Then to make it transferred to the destination, you need to again multiply with N4 over N3. Okay, so you need to multiply twice, 2 times. So we have N2 over N1 squared multiplied by N4 over N3 squared. Okay, so whenever you have a gear train, so here we call it gear train. Okay, gears yang bersambung banyak kali. So you need to consider the ratio, berapa banyak kali disambung tu kena darab dengan berapa banyak kali itulah squared, ataupun kalau nak transfer torque ataupun the angular position, you need to multiply the gear ratios for how many times the gears are connected. Okay, so in this case N2 over N1 squared times N4 over N3 squared. Okay, so this is for J. Now let's do for D equivalent. So the D equivalent, if you transfer all the D's of the gears, you cannot add the D on this shaft because on this damper. This damper is situated after the shaft J5. Unless if this D, if there is no shaft here, let's say no shaft, then you can add to this D. But because of this shaft, you tak boleh add dekat D. You cannot add with this D. So you need to create a new damper, okay? A new D. So DE, equivalent DE equals, so first we have D here. So this D on the gear is already on the destination. So this you don't need to do the impedance transfer. So first we have D, and then plus this D multiply with N4 over N3 squared. So we have D times N4 over N3 squared, and then plus the last D here. So you need to multiply with the gear trains, okay? So we plus D times N2 over N1 squared times N4 over N3 squared. Okay, so similar to the spring. So spring, we have K1 here. So we need to transfer the spring. So you cannot add the spring onto this K because this K, spring K2 here, connected after J5. So you need to create a new spring. So transfer K1. So we get K1 times N4 over N3 squared. Okay, so there is no spring here. So you don't need to add anything else, okay? Only K1. Now we have all J, D, and K equivalent. Now we can redraw the system, okay, to see or to visualize what is the final system after you transfer all the impedance. So we have a damper. So this is DE, and we have a spring, and this is KE, and these two are connected with shaft JE. And then this shaft JE has a damper D, which is this one, and also spring K2, this one. and these two are connected with the shaft J6 and a final damper D. Okay, so we have theta 6 here. Now we need to transfer so we have another torque here, torque. Now we need to transfer the theta 1 into the destination. So theta 1. So let's look at the formula again. Okay. So theta 2, theta 1 equals N1, N2. Okay, so to get theta E, say theta E equals, you need to multiply with the gear trains. So theta 1 times N1 times N2, and then N3 times N4. Okay, so you get theta E. So theta E here. So now the system becomes 2 degree of freedom. So you can solve it as usual. Okay, any question for question number 4? Okay, so if you have no question with question number 4, let's look at the last question. Okay, question number 5. Find the transfer function theta L over T. Okay, so theta L is located on the last shaft, while T is located on the first shaft. Okay, so in this example, you cannot use the last shaft as the destination, because if you choose the last shaft as the destination, then you need to transfer so many things. Like you need to transfer spring, the 1/10, and then the spring 2, and then you try to transfer the dampers. So you need to transfer 3 things onto this shaft. Okay. So it's easier if you can transfer into the middle shaft. Okay, so let's let's choose the middle shaft as the destination. Okay, let's transfer the left shaft first onto the middle destination. Okay, so because of this spring, when you transfer the spring onto this shaft, weirdly you can add the spring with this spring. Okay, only spring and damper. Okay, but for shaft you can add. Okay, but for spring, you cannot add them together. Tak tahu kenapa. Okay, one of the reason is that there's a degree of freedom in the middle here. Let's say we name it theta theta 2. Okay, so this theta 2 here is in the middle because, as I said earlier, when you have a spring and damper connected in series, then there's a degree of freedom in the middle. But in this case, we also have a degree of freedom here, let's say theta 1, and then here theta L. So theta 1 here, if you transfer this theta 1 onto the center into the middle shaft, theta 1 here is not connected with this damper. Okay, so it cannot become theta 2. When you transfer theta 1 to the middle section, it becomes an independent theta, or its own degree of freedom, because theta 1 here is only connected with the spring, gears, and another spring, but it doesn't connect with the damper 3 Newton meter second per radian. So by using the same concept, so if you transfer the spring into the middle section, and if you add this with the middle spring, then you are assuming that theta 1 is doesn't exist, okay, or hilang, but actually theta 1 is there. So what happens is that if you transfer this spring to the middle section, it should become something like this. A spring, let's say K equivalent 1, and then another spring, 2, spring 2 Newton meter, and here is theta 1. Okay, so if you add KE1 with the spring 2, okay, this is correct. So if you add them, then you assume there is no theta 1 here. Okay, because this is a torque, so you assume tak ada theta 1. So this is not correct. Okay, so the correct way is doing the first one here. Okay, same thing with the damper 200 Newton meter second per radian. If you transfer to the middle section, you cannot add with the 3 Newton meter second per radian because there's a theta L here. So theta L is connected with the two dampers, but not with the spring. So you need to have theta L here and the damper 200 or the damper equivalent 1. Okay, so the system is actually 3 degree of freedom system. So let's do the impedance transfer. So KE1 equals 1/10 times n destination 200 divided by n source 10 squared. So you get 400 440 Newton meter per radian. And then same with the damper equivalent. 200 times n destination, which is 10 over n source. So we get 2 Newton meter second per radian. Okay, so now we have the new system, the new drawn system with new spring and damper equivalent. Now you can find the free body diagram for this 3 degree of freedom, and then find the equation of motion in matrix form and try to solve theta L. Okay, so T equals 200 over 10. Okay, 20t. Okay, any question before we end these lectures?
Sir, nak tengok yang equation soalan 1 boleh?
Soalan 1.
Ha. Okey dah, sir. Okey,
Okay,
terima kasih.
any more question? Okay, so you can try the question first. If you are not sure, just ask me or Google or whatever. Okay. So that's it for tutorial number 4, and I think by the end of this week, maybe Friday, quiz number 2 will be released in Kalam. And please always look for Kalam. Okay, look into Kalam for the quiz question. And this Wednesday we will go into chapter 3, and we will see more detail about how to use the transfer function, and also how to see the behavior of a system according to a specific transfer function. Okay, I hope you understand up until now. Any question that you don't that you want to ask, just let me know. Okay, so that's it for today's lecture.
Doctor,
Thank you. Yes.
so the quiz, the due same as Sunday, isn't it?
I think so. I'm not sure.
Because Deepavali, doctor, that's why I'm just worrying about.
I'm not sure. I will ask the other lecturer first.
If Sunday means it's okay lah for me, due date, like the previous quiz one.
Yeah, because he will set the due date, so I will talk to him later and see what he
Okay,
said.
doctor. Okay.
Okay. Okay, so that's it for today's class. Thank you very much. Assalamualaikum and goodbye.
Thank you, sir.
Thank you, sir.
Thank you, sir.